In part one of these lectures on moments of inertia, we had used our definition of the moment of inertia, which we had derived, by the way, by finding the kinetic energy of a irregularly shaped object in space. And as we examine that object in the context of the kinetic energy of each individual part, we discovered that we could describe it, that total kinetic energy, as 1/2 the moment of inertia of the object multiplied by its angular velocity squared. So we had, in effect, derived the moment of inertia, the notion of moment of inertia from that. We then proceeded to find the moments of inertia in some particularly simple situations. A point particle, a hoop, for which we found the moment of inertia was mr squared, and for a rod about its center and a rod about one end. We discovered some generalizing things about that. For example, we learned that the moment of inertia of an object about its center of mass, an axis going through its center of mass, is the smallest moment of inertia that it can have, and also derived the parallel axis theorem, which allows us, once we know the center of mass moment of inertia, to find the moment of inertia about any axis parallel to that axis. So we achieved quite a bit. And what I'd like to do today is to continue again with finding the moment of inertia. In particular, I would like to find the moment of inertia of a disk like this one. Here I have a wooden disk about 10 centimeters in diameter and, 4 or 5 centimeters thick. And I'd like to find the moment of inertia about its center of mass axis. That is, if I were to spin it here, right about its center. And I know that the center of mass is in the center because the mass is equally distributed, and by the symmetry of the thing, not performing any integrals or whatnot, I can just look at it and realize that the center of mass of the thing is in the center. So I'd like to find the moment of inertia if it were to rotate about that axis, and I'm doing it as an exercise of finding the moment of inertia of a regular solid like this, to sort of expand our skill at doing such things, but also I have a purpose in mind. Pardon me, I have a purpose in mind for applying it to solving a physical problem, as we'll see going forward. So here I go calculating the moment of inertia of a disk. So I'll start here with a circle that represents the disk, and I'll appreciate that the disk has some thickness here, and I'll call that thickness in my calculation B, the thickness of the disk. It will turn out in the final result that the thickness of the disk will not be relevant to the moment of inertia, but I'll have to carry it along through the derivation so that I can make my arguments appropriately. So here I have the disk, it's circular and has a radius, which I'm going to call capital R. It's important here that I call the radius capital R, because I'm going to be performing my integral along a radius as a variable, and I'll use lowercase r for the variable and capital R for the constant radius of the disk itself. It's really critical that I do that, because as I perform the integral, if I don't get my notation right, I could inadvertently cancel some r's and I'll end up with the wrong dependence, and you'll see that going along, and perhaps I'll reiterate it as I go. So here I have the disk of radius capital R, and I know that when I do these sorts of things, remembering back to finding center of masses, that very often it's good to know the density of a thing. Well, this disk has a particular mass and it has a particular volume. So its density is easily calculated as the total mass divided by the total volume. So here I'll take the mass and divide by the volume of the disk in my diagram here, which certainly will be its cross-sectional area multiplied by its thickness. I very often, when I'm doing derivations, think of the volumes of right regular solids as their cross-sectional area multiplied by their extruded distance. Well, the cross-sectional area of the disk, of course, is the area of a circle, which is pi capital R squared, the entire area of the disk multiplied by its thickness, which, as I said, I'm going to use here B as the thickness of the disk. And so I'm going to perform my integral that defines the moment of inertia. The moment of inertia is equal to the integral of r squared dm. And so immediately, I have to figure out how I'm going to make this into an integral that I'm going to solve. I need a relationship between r and the differential of mass dm. And again, recalling the techniques that I used for center of mass, I realized that what I'm going to do here is find some way to take my disk of mass here and slice it up into differentials of mass. And those differentials of mass, somehow I want them to be related to radius vector drawn from the center of mass of the thing outward. Well, that's a little bit trickier to do here, because You might, when I did moments of inertia, for example, of a rod, I simply sliced it up along the x-axis with differentials dx containing a mass dm, which is quite simple to do. But here it's a little bit more sophisticated. So what I'm going to do here is I'm going to slice the disk up into annuli. An annulus here is just sort of like a circle with an interior radius and an exterior radius like this. And it has a thickness that is a differential of the radius. So here it is, my annulus of radius r. Now when I draw the radius r, you might wonder, is it the inside radius or is it the outside radius? It turns out it doesn't matter. Because the annulus is infinitesimally thin, and here in my diagram I've made it thick enough that you can see it. It's certainly not conceptually what I'm doing. Conceptually what I'm doing is it's infinitesimally thin. It has a thickness dr. Then the inside radius and the outside radius are indistinguishable the one for the other, which is a fact about this that I'm about to take significant advantage of. So here I have a little differential dr that creates this annulus. This annulus is an infinitesimal fraction of the total mass m, and so inside that radius dr is a differential of mass dm. And I'm going to take advantage of the density just as I've done in the past, where here I've defined the density as the mass per unit volume. It's certainly true, but it's also true then that it's the differential mass per differential volume. So rho is equal to dm dv. Well, in order to finish this off, I have to find a way to express the differential of volume. It's the volume of the annulus that I've drawn there in my diagram. Well, the annulus, I'm going to find its volume the same way. I'm going to find the area of that annulus and then multiply the area by the extruded distance b to give it the thickness that it needs. Well, a trick that I learned early on when I was solving these sort of things, or a way to think about it, is that since this annulus has the same inside radius as the outside radius effectively, because dr is so small, that means the circumference of the inside circle of the annulus and the circumference of the outside circle are the same, which makes the annulus like a rectangle. So what I tend to do in my mind when I'm thinking about these things is I'll take the annulus here and I'll just sort of grab hold of it and break it. Just pick an arbitrary spot and snap it and then lay it out flat like this here, and it becomes a rectangle. I've just taken the thing and I've bent it out, and you say, well, you can't do that, you see, because the sides aren't the same. Yes, they are. Because the inside radius has a circumference 2 pi r and the outside radius has the same circumference 2 pi r because dr is infinitesimally small. So it is a rectangle whose length is 2 pi r and whose width is dr. Therefore, I can write dv, the differential of volume, as that area, 2 pi r times dr, the area of that rectangle, multiplied by the thickness, which is b. That's just, again, the thickness of the disk that I'm solving for. And so here, that gives me my differential of volume in the denominator. So I can do the trick that I've done many times before. This gives me a relationship between dm and dr, allowing me to transform my integral, the integral of r squared dm, into an integral of dm to an integral of dr. And so I'll go ahead and make that substitution. Now, my density here is full of constants. 2 is a constant, pi is a constant, and b is a constant. I'll pull all of those constants out of the integral here, 2 pi rho b. The integral of, now I have the integral of r squared, but my volume here has an r in it, so that's going to become r cubed dr. Once I've made that substitution, dm is equal to rho 2 pi r drb. Factoring all the constants out in front. Now, I guess I should name the limits of integration at this point. I'm integrating this from the innermost of the disk, which is the center of the disk, the center of mass of the disk, integrating all the way out to the furthest extent of the disk, that is to capital R. You see here why it's important that I distinguish between the radius of the disk itself, capital R, and the radius of the annulus, which is the variable. If I had conflated these things, I'd be in a little bit of algebraic trouble right now. So once again, I find myself in a situation where the integral that I need to solve is very, very simple. It was the setup of the integral that was challenging, because the integral of r cubed dr is easily solved. It's going to be r to the fourth on 4. So I write my constants again, 2 pi rho b times r to the fourth over 4 here, but I have to evaluate the limit 0 to r, which is simple to do because at 0, the thing is 0. So my result is 2 pi rho b r to the fourth, the radius of the disk, over 4. I'm not done yet, though, because as I've done in the past, I'm going to take my original density, the density of the disk overall, the mass per unit volume, which is m over pi r squared b, and I'm going to insert that density in, and I'll find quite a bit of simplification. So inserting the density, I have my constants 2 pi b times that density, m over pi r squared b, right there in front, r to the fourth on 4. And I see I have quite a bit of cancellation. I have this 2 cancels the 4 in the denominator to a 2. I have a pi cancels a pi. I have an r squared cancels all but 2 of the r squareds in the numerator. And the b's, of course, cancel, which I predicted that they would. It turns out the thickness of the disk is irrelevant. I'm calling this the moment of inertia of a disk, but it could very well be the moment of inertia of a cylinder if I extruded it out far enough that we sort of look at it and claim that it was not a disk anymore but a cylinder. I don't know what critical point that is, sort of arbitrary where you call it a disk or a cylinder, but they're the same according to this moment of inertia. What I'm left with is the moment of inertia of a disk is 1/2 mr squared. And we see it was a little bit more challenging for me to derive that moment of inertia than any of the other moments of inertia that I've tried to calculate. That's the last one that I'm going to demonstrate in lecture. But of course, there are many more that I want to know. You can imagine, I'd be very interested to know what is the moment of inertia of a sphere, both a hollow sphere and a solid sphere. And I might want to know the moment of inertia of a rectangle, about its center or about one side. One side would be interesting because a moment of inertia of a rectangle about one side would be like a door, which is certainly an object that rotates and be of some interest. So there are many more moments of inertia, and I can sit down and set up the integrals and solve for those. And again, I can also look in any textbook worth its salt, and I'll see a table that describes many useful moments of inertia for solving problems. For the moment, I'm done solving for moments of inertia. I would like to see how I apply moments of inertia to the solution of problems. Recall a problem that we've all solved many, many times of a block sliding down a frictionless incline. The block begins at the top of the incline with some unction of gravitational potential energy, mgh, and then it slides to the bottom, and at the bottom it has only kinetic energy, 1/2 mv squared. If I do that in my mind, the law of conservation of energy says that mgh is equal to 1/2 mv squared. The masses cancel. I do a little bit of algebra around, and I find a very familiar result that we've all written, everyone here has written on a paper at some time, solving a problem, that the velocity at the bottom of the incline would be equal to the square root of 2gh. Which is a very, very simple problem to solve, very common problem to solve. But I suppose it did not, in your mind, create any curiosity or concern that it was always a box, and it was never an object that was allowed to roll down a ramp. So that is the problem that I would like to solve, and I'll see immediately that I have to be a little bit more careful in how I observe the conservation of energy in that case. So let me consider here that I have a very familiar inclined plane that's inclined relative to the horizontal with an angle theta. And what I'm going to do is place a disk like this one that I have here. I'm going to place a disk at the top of the incline. I'm going to allow it to roll down. Now my objective here is to find the speed at the bottom of the incline. And in doing so, I'm going to have to take advantage of what I've just derived here, that the moment of inertia of a disk is equal to 1/2 the mass of the disk multiplied by the radius of the disk squared. So I want to find the velocity of the disk at the bottom. And so I'm going to do the law of conservation of energy, that the initial energy of the disk, plus or minus any work done by non-conservative forces, is equal to the final energy of the disk. Now there's no work done by non-conservative forces here, so this is a situation that we might describe as the energy being conserved. So what kind of energy does the disk have in the initial configuration? Well, it has gravitational potential energy, but how should I write that as an expression? How do I measure the gravitational potential energy of an object that has a physical extent? Well, we've done it before, we just weren't thinking about it. How did we describe the gravitational potential energy of that box sitting at the top of an incline? We just sort of assumed that the size of the box didn't matter, but indeed it does. Recall when we were studying momentum and we discussed systems of particles, that we realized that a system of particles, like this disk that has physical extent in space, can be described as the total mass located at the center of mass position. Now for this disk, naturally, the center of mass position is the center of the disk. So naturally, if I want to measure the gravitational potential energy of the disk, the location of choice is the center of mass of the disk. So as the disk rolls from the top of the incline to the bottom, the center of mass will drop a height h. And so that's how I'll measure the gravitational potential energy. So I'll say that that from the top to the bottom it will descend to height h. And so I'll write the initial gravitational potential energy as the mass of the disk mgh. That naturally will be equal to the kinetic energy at the bottom. But now here's the difference. Here's the new physics. The kinetic energy at the bottom is two kinds of kinetic energy. Indeed, the center of mass of the disk will be moving with some velocity v at the bottom of the incline, and that's the velocity that I'd like to find. But also, because it is rolling, it will be rotating simultaneously. That is what I'm implying here, is that at the bottom of the ramp, it has two kinds of kinetic energy. Translational kinetic energy, which I'll call kT, and rotational kinetic energy, which I'll call kr. So I have to write this as the sum of the translational kinetic energy, 1/2 mv squared, plus 1/2 I omega squared. Two different forms of the kinetic energy. Indeed, it's the same kind of kinetic energy. It's all mass in motion. But we now look at the motion as two linearly independent parts, the translational part of the motion and the rotational part of the motion. So now if I want to write this, I'll write this expression again, but what I'm going to do is flesh out this rotational kinetic energy, because indeed, I've just found, through a little bit of labor of calculus, what the moment of inertia of a disk is. So let me write that mgh, the initial gravitational potential energy, would be equal to 1/2 the mass times the velocity squared plus 1/2 of the moment of inertia. So I'll write here in parentheses 1/2 mr squared times omega squared. Omega is the angular velocity. And so what I'm going to do here is make a substitution that might trouble you just now. I'm going to appreciate the fact that my omega is v divided by r. That is, v is equal to r times omega. Those kinematic relationships between the translational velocity and the angular velocity. It would be totally appropriate for you at this point to say, wait a second, how do you know that in this case that's particularly true? Well, I'm going to cheat for a moment, as I do sometimes, just because of the order that we do the lectures and discuss these things. And I'm going to ask you to trust me for a moment that here it is appropriate for me to replace omega with v over r. Some of you, it's not bothering you at all. You say, yeah, sure, go ahead. I saw an equation one time that said that v is equal to r omega, so clearly omega is equal to v over r. Knock yourself out. But I have to be really particular about that condition. I'm going to leave that particularity for another lecture. So instead of writing omega squared here, I'll write v squared over r squared. And now I see that across the board I have a great deal of cancellation that takes place. The m's will cancel all along, and this r squared here will cancel an r squared in the denominator. And so looking at this, what I'm left with is that gh is equal to v squared over 2 plus v squared over 4, which is clearly 3/4 v squared. Now, it was my goal to find the velocity of the disk at the bottom of the ramp. And so I solved for that, and that's v is equal to the square root of 4/3 gh. 4/3 gh. Now remember, if this had been a box, and I'd slid it down, the result that I get, the very familiar result, is that the velocity at the bottom of the ramp would be equal to the square root of 2gh. But here, I find that it now has a lesser velocity. When the disk rolls, it gets to the bottom with a velocity that is lesser than the velocity of a box of equal mass sliding down a frictionless incline of the same angle. There's less velocity at the bottom, less speed at the bottom of the ramp. Well, that's easy to account for if you take a moment to think about it, because you might make an argument that some of the gravitational potential energy at the top was transformed into rotational kinetic energy, and rotational kinetic energy does not contribute to the speed overall. An object can have rotational kinetic energy here and not translate, and so it doesn't go anywhere. And so there's no speed of translation associated with the rotational kinetic energy. So, because a fraction of that energy is transformed into rotational kinetic energy, the translational speed at the bottom of the ramp is understandably less as a result. Well, I'm curious what would happen if I roll other things down ramps. And so what I'm going to do, you see I have here this steel hoop. And this steel hoop happens to be of a very similar mass. I'm not claiming that they're exactly equal. They are very, very similar in mass. But it's okay, because notice that the final velocity here didn't depend on the mass of the disk at all. So it's all right. And as you can see, these two are of very similar radius, practically, virtually, exactly the same radius. So I have a disk here, which has a particular mass and a particular radius, and a hoop of the same mass and the same radius, but they do not have the same moment of inertia. They have the same quantity of inertia, they have the same mass, but they do not have the rotational inertia because, in the last lecture, I derived that the moment of inertia of a hoop was mr squared, effectively twice the moment of inertia of the disk. And that makes sense because the mass of the hoop is distributed around the outside, further away from the axis of rotation. So what I'm going to do is exactly the same calculation again, except I'm going to place the hoop at the top of the ramp. So here I'll draw an identical incline, the same incline angle, except now I'm going to draw at the top. I'm going to put a hoop here, and the moment of inertia of the hoop I know is equal to mr squared. It's still true that I measure the gravitational potential energy of the hoop by its center of mass point, which is the center of the hoop. And so I'm going to write the conservation of energy. I can actually move ahead a couple of steps here. I don't have to repeat myself over and over again. The gravitational potential energy that the hoop has at the top of the ramp, which is mgh, is equal to the final kinetic translational kinetic energy, 1/2 mv squared, plus 1/2 I omega squared. And so I'm going to make the same substitution again. I'm going to plug in I, but this time I'll plug in the moment of inertia of the hoop. And I'm going to plug in omega is V over R again. So what I'll write is mgh is equal to 1/2 mv squared plus 1/2 mr squared v squared over r. And I have the same thing here, that the masses cancel, and there they go, and the r squareds cancel. So now I have, obviously, I'm coming to a different result. gh is equal to v squared over 2 plus v squared over 2, which is just v squared. So I find that the velocity of the bottom is the square root of gh, is the square root of g times h. It's even less. Now, the hoop has an even lesser velocity at the bottom of the ramp than the disk did, and the disk has a lesser velocity than a box sliding down a frictionless incline would. Well, what's the difference here? Clearly, the difference is the hoop has a larger moment of inertia. So what does it mean? It means that since the hoop has a larger moment of inertia, that a greater fraction of the initial gravitational potential energy is transformed into rotational kinetic energy. And so if it has more rotational kinetic energy, it means it has less translational kinetic energy, which means its velocity is naturally less. And a thing that I like about that, this little demonstration here, is that I have these two objects, like physically with me right here. I have the disk and the hoop, or the disk and the hoop here. Same mass, same radius. And I have an incline here. I can use this table. And I can have sort of a race between the two. I can put the disk and the hoop side by side on the table and let them roll from one end to the other and observe the outcome. The funny thing about the thing that I like about this is a little moment. I have a little moment, physics moment here, where I enjoy thinking about the fact that I already know what the outcome is going to be. When I lift the end of the table, I know what's going to happen. I know that because the disk moves with a higher final velocity than the hoop does. The final velocity of the disk is larger than the velocity of the hoop because the disk's final velocity is the square root of 4/3 gh, and the final velocity of the hoop is simply the square root of gh. So the disk moves faster in the end, which means it moved faster at every instant in time. And I have no need even to do any kinematics. If it's going faster the whole time, then it will reach the bottom of the ramp sooner. That is, if I think of it in the context of a race, then the disk will most certainly win. And so I already know the outcome. Through reason and the careful, logical, rational application of my physical laws, I'm able to make a prediction about nature, context that I've never observed before. Of course, that's a bit of a lie. Naturally, I have observed this before, but you, the audience, have not. And so even though it hasn't happened yet, we know what's going to happen. We know. So I can just take these and put them away now. We don't actually have to lift the end of the table and watch the race happen. But we appreciate the fact that indeed, at the end of the day, physics is an experimental science. So everything that I derive theoretically, I would hope to observe it experimentally in the laboratory. We're not going to go through the trouble to measure the velocities to make sure they match us. Indeed, we would find experimentally that they were different because of some factors that I hadn't taken into account, viscous drag, for example, and the differences in friction forces and so on that take place. But so what I'll do is I'll place them here, one next to the other, the hoop and the disk, and I have to get them to try to stay still at the same time, and then I'll simply lift up the end of the table, creating an incline, and I find quite dramatic indeed. But I find that the disc wins the race to the bottom, although the hoop succeeded in making it further across the room ultimately. The disc reaches the bottom of the ramp first because it has the lesser of the two moments of inertia. So I find now that I can solve much more sophisticated problems, because now I realize that I need to include the moment of inertia, that is, I need to include the rotational kinetic energy. Just an aside to this of how critically important it is. A couple of years back, we were doing some experiments with young folks where they were building a kind of vehicle made out of a mousetrap, where the spring energy that's in the mousetrap is used to propel the vehicle forward. And so it might be interesting to do it experimentally as an issue of conservation of energy. There's a certain amount of spring energy contained inside the mousetrap when the mousetrap is set, and that should become a certain amount of kinetic energy of the mousetrap car at the end. So interesting thing that happened is we calculated how much spring energy. We did some experiments to try to determine how much spring energy is stored in a mousetrap spring. And then we tried to figure out, based on the mass of the car, what the velocity should be, and then we measured the velocities and found that they were completely wrong. The velocity of the mousetrap car at the end was much, much lower. And after a few moments of thinking, I began to wonder, this mousetrap vehicle that has wheels that are made out of CDs, like compact discs plugged onto the side of the thing in order to act as the wheels. When the car is moving forward, how much rotational kinetic energy do the wheels actually have? What fraction? It turns out, a little calculation, back of the envelope sort of thing, and I discovered that by the time the mousetrap car is going along at its maximum speed, almost half of the kinetic energy that it has is in its wheels. And so if I would do an experiment involving a car rolling down a hill or something like that, whereas I would not have considered the rotation of the wheels before and the rotational kinetic energy they have, I realize now that I must do that in order to get the correct solution to some of the problems that I might like to solve, technological problems or engineering problems of that sort.